Okay, so thank you everybody for your patience. I'm sorry we had some connectivity problems, but we are back here with Professor Marcel Pelgrom. So please enjoy the presentation.
Okay, thank you again. And as I said when starting the first time, I do hope that you're all a little bit safe for this corona virus stuff, and I hope you stay healthy. I'll talk today a little bit about ADC performance limits, fundamental stuff in this talk. Obviously, we have to satisfy the lawyers a little bit, so I hope the lawyers are happy now. And let me make sure that now you are happy too. Well, analog to digital conversion is a very often used process. We see it everywhere. I say always to my students, in my laptop there is one Intel inside, and there are at least 12 A to D converters inside. So it is a major step between the physics domain and the numerical domain. We need 3 steps to do that, to convert. Basically, that is the so-called sampling process from time continuous to time discrete. There is the quantization from amplitude continuous to amplitude discrete. And we should not forget that to every numerical value, there is a physical quantity in the background. And so only 125 only means something. At the moment, you know that 1000 is equal to 1 volt. So today I want to talk a bit about sampling and quantization aspects. In sampling, we will talk about Fourier and Jitter. Quantization, I will discuss non-idealities, mismatch stuff. You know, that's one of my hobbies. Yeah, and then finalize with a little bit of an overview and the conclusions. Well, I guess everybody is familiar with the so-called Nyquist theorem. Mr. Harry Nyquist over here was an engineer from Bell Labs, and via a little bit strange path, he became the name bearer of the Nyquist-Shannon sampling theorem, which basically says that if you take samples from an analog signal, from a time-continuous signal, then you need to make sure that the bandwidth of that signal is smaller than half of the sampling rate, because in that case you can always reconstruct. This is probably familiar to most of you. Just wanted to point out here that there is something that is perhaps not so familiar, a paper by Landau in 1967, where he basically showed that for a large number of other cases, like non-uniform sampling, you can also derive a sort of Nyquist theorem under certain boundary conditions. For those who want to dive deeper in this field, that is a very interesting paper. The inequality formulated by Nyquist and Shannon is just one of several inequalities that we face. Another inequality is the so-called Fourier uncertainty. And this has no relation with physics. It is a purely mathematical construction. What is shown there? Yeah. Oh, my writing is not too good. And basically, that says if I have an observation window delta t, then the quality or the certainty of my frequency content is given by delta f. And delta f times delta t is smaller than half. Some people use that 1 over 2 pi, but the most used formulation is half. And that is an important part for us also, because it simply means that a short observation window simply translates in a poorly defined frequency quality. And that means that for all kinds of observations that we do, we need to stretch the observation window preferably to infinity, because if the observation interval is infinite, then we have a very low uncertainty in the frequency. This is something that pops up if you take an FFT from your A to D converter and in several other aspects while doing measurements. This is a pretty fundamental mathematical theorem, but one that carries over in physics because there's a certain Mr. Heisenberg who took the fundamentals of that uncertainty theorem and extended that and applied it into a theorem, into a physics theorem that you may know in various forms. So you have here delta energy times delta T is must be bigger than Planck's constant divided by 2 pi. You have also the same for delta momentum times delta position, that must be bigger than that. And so there are quite a bit of reformulations of Heisenberg's uncertainty theorem. I'll show you in a minute that it also applies to A to D converters. And despite the fact that this was derived in the 1930s, people struggled a lot with what it meant. And so there's an interpretation that says it obviously takes delta T to measure a state, say a voltage level, with a certain accuracy. And that would mean that it is a measurement limit. But in the recent 2 decades, there is another interpretation. And that interpretation is much more fundamental. Basically, it says in a little bit complicated situation, when 2 states are separated by an energy delta E, it takes delta T to go from one state to another. This is not charging. This is really fundamental quantum physics. Yeah, but this has a very important side effect because it means that it is a fundamental speed limit for A to D converters. When 2 states are separated by an LSB, then it simply means that there is a background speed limit to go from LSB to LSB plus 1 given by this theorem. Let me dive a little bit deeper in there. So don't worry, I'll make sure you get the slides later on so you can go through this at will. But I made here a little example, and just to give you a little bit of flavor of what that Heisenberg statement means, is that it equals the energy of, for instance, a 14-bit LSB on a 10 femtofarad capacitor. And though I know that 14-bit A to D converters are not using 10 femtofarad, but we are seeing papers where there is, for instance, 150 femtofarad total capacitance used. So we are getting close. Yeah. Now, if you then say, okay, let's translate this into power, then it turns out that, for instance, for a say 100 dB signal-to-noise ratio, 100 gigasample A to D converter, it means that overcoming the Heisenberg limit takes 11 milliwatt, while overcoming the thermal noise in the same situation requires 2 watt. So there's still some space, but it's getting closer. Yeah. Here is a plot that I will use a little bit more often later on. On the horizontal axis you see the bandwidth, on the vertical axis you see the signal-to-noise ratio. And here are, in the dotted lines, are the powers that are needed to overcome with your signal a certain level. So if I want, for instance, 80 dB and say 3 megahertz bandwidth, then I need 1 microwatt signal power to get that realized in the presence of thermal noise. Then we see that over here was the example I was just making. Here is the Heisenberg lines, and here are the thermal noise lines, and you see that we are we are still okayish, yeah? Say over here we need 1 watt for the thermal noise and 1 milliwatt for the Heisenberg, so what the heck? Well, not for us, yeah? While Walden in 99 still reported 4 orders of magnitude, we now see in the plot there's 2 orders of magnitude, and so when your grandchildren start working in industry, I would not be surprised we see the first problems with for this fundamental limit on Heisenberg. Yeah. So at this moment we do see already A to D converters penetrating the 100 gigahertz domain, and I would not be surprised that in 20 years we will see problems in this domain over there. Well, Fourier. I always tell my students, you had Fourier in your first year bachelor, get back to that class and study Fourier again. It is so important to understand A to D conversion, because Fourier plays also a role in another function that we need for an A to D converter, and that is the Alias filter. Well, if you try to do a conversion of this bandwidth here in the lower left, then obviously you don't want all these spurs and whatever stuff you have over there folding back into your baseband. And that means I need a filter to kick out these guys. And I need a certain amount of suppression, and there are only 2 ways to improve that suppression. And the first way is to improve the order of the filter. Yeah. And the second way is to create more distance between the bandwidth and the sample rate, or better said, I must move the sample rate in the higher direction. And that means that this is a very, very unpleasant boundary condition in this field. Most people know this, but there is something that a lot of people forget about this. And that is that, again, purely from math, no physics involved, no electronics involved, purely from the mathematics, a sharp limit in the frequency domain translates in the sine x over x behavior in the time domain and vice versa. A block in the time domain creates a sine x over x response in the frequency domain. And this is very, very ugly, because it simply means that when you apply a very sharp filter in your alias filter, then you essentially ruin the phase of your signal. And that means that when you want to have a certain signal going in, yeah, then you will get a phase distorted signal coming out. Yeah. So your frequency components are still there, but they're all shifted with respect to each other, and you don't get a clear pure again. So this is one of the reasons why you never can operate a Nyquist. Actually, we found out the hard way in Philips just at the moment when I entered the company in 1997. Philips was basically ready to promote the compact disc. Yeah, today it's almost a museum piece, but at that moment it was really really something really good. And unfortunately, in the compact disc, we want 20 kilohertz of bandwidth at a sample rate of 44.1 kilosample per second. And that means that you have here only 4 kilohertz to do a very sharp filtering. And you directly now recognize the connection to the previous part. That filter is going to really be a distortion. And that means that these filter characteristics over here are really disastrous. Why do you need that in a audio equipment? Now, the problem in audio is that if this energy from your sampling process, if that energy enters here your tweeters, you get a tremendous nice fire, and then the tweeters are blown, and probably also your amplifier. So later on, this point was solved by digital oversampling, but it was a major conceptual miss in the very first CD players. Well, noise, KT noise. Well, one of the problems I face with my students is that everybody says, noise, oh, I know that is connected to the resistors. It is 4 KT R times the bandwidth, delta bandwidth. And I have to tell them that that's rubbish. Yep, that's simply not the case. A thermal noise is basically due to the energy distribution over the electrons and has nothing to do with a resistor. A resistor just confines the current flow and nothing more. In a theoretical resistor, there isn't even a single electron. Yeah. So the real way of looking at it is that in a system with 1 degree of freedom, the kinetic energy is kT over 2. And we electronic engineers know that the energy equals CV square over 2. So if these two are equal, then obviously you know the total amount of noise of this system. And that is related to the capacitor, the container of the energies of the electrons with all those energies. And that means that essentially the right way to approach this noise stuff is to look at KTC in your circuit, yeah, and realize that the KTC is the area of here this noise spectrum, and that what we use as 4 KTR, that is the recalculated spectral density associated with this effect. And yes, indeed, if I nicely take the integral over this noise, I get very nicely again the KTC, yeah, terms back again, and it works. But at the moment you are tested for a job application, and I put a resistor in front of you and say, here's a resistor. How much thermal energy does it have? And don't start talking about 4 KTR and simply say nil, because a resistor on itself has no noise properties. The noise source attachment to a resistor is a modeling trick, and it is important to realize in a lot of situations to check the KTC noise. I think if you want a little bit more explanation on that, Professor Moorman has given some interesting comments on that in the Solid State Circuits magazine of a few years ago. And he basically analyzes circuits by analyzing the capacitor. He analyzes noise properties by analyzing the capacitances in a circuit. We have to sample the noise, and that is creating quite a bit of fuss also with my students. Because if you have here a time continuous noise spectrum, where here you see the time paragraph, then you can subdivide that in the Nyquist zones, and then after sampling you get very nicely the stacking of these spectra. Goes up much further than 6, of course, but that's just for simplicity here. Well, which was something that was not so simple, was to get this here mirrored in PowerPoint, but that's another story. Yeah, and so I ask my students always, if this is the energy before sampling and this is the spectrum after sampling, then I must have multiplied my energy in my noise. Yeah, you can see that here, eh? And then my students get really, really confused because they don't understand that this is, again, a model that we use in digital signal processing and has not a real physical significance. You can nowhere in your system point at the signal and find this. What you can do is go to a reconstructed version of these samples, and then you find out that this reconstruction acts as a filtering, and with the optimum filtering, for instance a zero order Holt in this case, you will get back exactly the same amount of noise energy as we started with here in the analog domain. A typical question for a job application interview of a PhD student, because I think those students should understand this phenomena here. A little bit further in the basics of A to D conversion. We have to take decisions in A to D conversion, and what we use for decisions is a latch. This is a very simple latch with a cross-coupled pair loaded with capacitors and a clock, in this case a negative going clock to activate this. And if you activate that, then the voltage difference on the node, here for instance is a starting voltage, a fraction of an LSB. At the moment the clock hits, then basically you get a linear response, because you basically get at that point a positive exponential function that is still in the linear description until you hit over here the power supply or the ground line. This is an important little picture because it means that within a certain amount of time I need to grow to a certain level. Yeah? If I do not match that level, then our digital friends won't know what they get, because they will get something like that. Now, is that a 0 or a 1 or what is that? They don't know halves, you know. And so what the problem in every A to D converter, and specifically the very fast one that we see over the last year, is that this alpha is too small. And when I talk about too small, then I don't mean 1% or 10%, but I mean 10 minus 8 or even 10 minus 15, as at this moment is required in data centers for Google and for these kind of people. Now, if this is a too small starting value and you don't reach a decision level, then we talk about metastability and a bit error rate that is associated with that. So what you have to do in order to look at this type of circuits is to check for the settling tau that is associated with this little circuit, and that was shown in the previous slide. And here is a simulation, and basically this is a strong arm comparator. This is a very popular type of comparator, and this is a strong arm comparator from a very large company that one of my students was able to investigate. And what you then see is that if you have a starting value between the two nodes, so this is the delta V node, as you can see over here. Yeah, if you have a starting value of say 100 millivolt, then basically you don't lose much time, because the 50 picosecond over here is the post-processing delay, but you do not lose any time because of the settling of this guy. But if you go to smaller node values, then you see that the settling starts to increase. And the slope of this line follows an exponential behavior, because you see that the horizontal axis is a log scale, and you can directly derive that the tau here is something like 9 to 10 picoseconds. And that's devastating. That's really a big problem, because suppose you want a communication level bit error rate, you want 10 bit, then you need something like 25 tau or 250 picosecond or for 2 gigasamples per second in order to process a gigahertz of bandwidth. 1 gigahertz of bandwidth. Now, Heisenberg wouldn't be afraid of that, you know. And in a 28 nanometer CMOS process, the tau is down to 7 picoseconds, but basically it limits for 10 minus 8 bit error rate, it limits the maximum sampling speed to 2.7 gigasample. This is a very, very ugly sheet because it really creates a lot of problem if you want to really go high speed. Well, you can do something about that. You can go to higher currents. You go to low parasitic capacitances. But basically, the big drive, the big fundamental drive for going into time interleaving, putting A to D converters in parallel, is this slide. Yeah, because by time interleaving, you can keep individual comparators, individual ADCs below this border, while the total can be of a much higher part. Well, I'm sure now 2 or 3 of you are typing, yeah, but in a new process, aren't we going to be better? I have bad news for you. That's not going to be the case, at least if you follow the last ITRS roadmap. And here you see the saturation current of the transistors. And to your surprise, you basically see that saturation current is predicted to go down. Yeah, here we are in the say the 16 nanometer FinFET. This would be the 8 nanometer FinFET, perhaps the delayed 10 nanometer. And over here we are at the next generation. And you see that the current, the expected current for these very small devices is going down. Yeah, but then the tau, basically the capacitor, yeah, that is not going to change much over the years. And that essentially means that we do not have to expect a very large improvement in speed in the new processes, unless somebody comes up with really the next generation. So today we have FinFET in production. We have the sheet FET in as most likely successor, but we need something much faster than all of that. So basically, any improvement that we have to look into A to Ds must come from architectural innovations like the previously mentioned time interleaving. Well, let me move to the last of the sampling problems, and that is probably also one of the most nasty ones. Yeah, Jitter, in my 41 years of industry experience, Jitter is one of those sneaky snipers that shoots at you in the most impossible situations and creates trouble. The point is that Jitter is not just noise. Jitter can cause distortion, can cause spurious, and believe it or not, it can cause DC offset. Jitter is the random misplacement of sampling moments. So normally you want equidistant sampling moments, but due to a number of reasons like thermal noise, power supply rejection, parasitic coupling, component mismatch, you get misplacement of the sampling moments. There are quite a bit of possibilities to define jitter. In A to D converter, we mostly use cycle-to-cycle jitter. So if this is a sampling moment and that is a sampling moment, then basically we are interested in the difference between here and there. But on the other hand, if you look, all of you are now looking at a screen, and if this screen is being built up with writing lines on your screen, then basically you go all over this screen to here, and then over here you don't want to see any jitter popping up. Yeah, now that is what people call long-term jitter, and in display this is a very important parameter. So there are differences, but I will concentrate here on the cycle-to-cycle jitter for A to D conversion. Jitter and phase noise are brothers in arms. Yeah. Essentially, jitter is the time domain representation of phase shifting, and phase noise is the frequency representation of time shifts. And there is a very interesting paper by a certain Mr. Drakris, yeah, in a rather advertisement kind of journal, yeah, but really worthwhile going into. And they're used as a starting point that if you have a sine wave, yeah, and in that sine wave there is jitter and there is phase noise, then basically those things have the same effect. And that means that there is that you can more or less trade off phase noise versus jitter versus phase noise. And that leads to a little bit of mathematical manipulations, but basically saying that your phase noise relative to your sampling period is the integral of your phase noise over here. Well, obviously you can translate from here to there, but it is not possible to go from here to there, because if you have 1.4 picosecond phase noise, you do not have sufficient information to subdivide the phase noise in these different regions. Yeah, so keep in mind, phase noise and jitter are basically representations of a similar phenomenon. From phase noise, you can always get the jitter, but not the other way around. Well, what happens at the moment you have phase noise? Well, basically a misplacement of your sampling moment leads to a different value of your sampling value. And this delta A over here is the error, and if this over here behaves in a certain way, then this delta A will follow that in a similar way. We basically in A to D converters always use sine waves to characterize stuff. That is really from the early ages. And from those ages we have also this jitter formula that is probably pretty well known. Yeah. Note, by the way, that jitter is a ratio between the amplitude and the jitter magnitude. And the point here is that if this amplitude is twice as large, then obviously the error will be twice as large as well. And that means that the signal to noise ratio is independent of the amplitude. And this is a very important property that allows you to characterize whether you have jitter in your system or whether you're still looking at sample noise. Multi-tone signals, like we use in mobile phone communication, then you have less jitter. In current ducts, for instance, you have more jitter, but all of these things depend on specific application parameters. This is the jitter again in my preferred plot. Now on the horizontal axis is the frequency, and here is the signal to noise ratio associated with that. And you do see here that jitter is really a boundary condition. Eh? If you look at 10 megahertz, then basically there is no way to get better than, in this case, 100 dB of signal to noise ratio, simply because the best reported jitter in a practical design is 50 femtoseconds, and that means that this is basically impossible. So this here is terra incognito. So this is unknown field for the sampling people. This is here you can be sure you can still make a good living when you do RF, yeah, for quite a long period, I think. Well, if you look at jitter, then a lot of people talk about that this trip point over here is affected by KTC noise, by 1/f noise, and all this kind of stuff. I'm not so sure of that. Yeah, if I look at the practical design, this is a simple inverter from a library, and if you do the simulations, then you see that you end up with something like 25 femtosecond RMS, and yeah, obviously that's not nil, but if you look at another problem, for instance here, if your power supply is moving around, yeah, then you directly see you run into much larger values. So whenever I see a problem in Jitter, then my first my first point of attack is that I want to see how clean is the power supply, and aren't you running into real trouble over there? And you won't believe it, but how often I see that people push clocks for A to D converters, for switch cap circuitry, for class D amplifiers or whatever more. They push clocks through the digital block over there. Now, this is a huge mistake. Yeah, you are never allowed to process your sensitive clocks in the digital domain, because that directly runs you into this type of issues, and you basically have lost the battle before you even have seen a single enemy soldier. Yeah, that's not the case. So, in order to give a little bit of an idea on how this jitter is moving over the years, I have here a list of Olympic years. Now, okay, I see my error over there. I need to put here 2021. Yeah, but I hope you forgive me that I leave that for this moment. I will leave that in. And if we now inspect again the plot, here is the signal frequency on the horizontal axis, the signal to noise and distortion, as is reported on the ISSCC, and I steal here the data from my good friend Boris Moorman. And then if you now look at let's say the oldest guys over there, then you see already over there a green one, over there a green one, over here a green one, and you see, for instance, that today, this year on the ISSCC, you see over here what? No, okay, this was a bio paper, so you can forgive them, but look at that, huh? That's so much margin left. This year there was only one paper, and I think it was the paper from Ahmed Ali from Analog that approaches this line. And yes, let me a little bit proud. My student in the KU Leuven last year on ISSCC had this paper over here, and I just want to show you a little bit what we did in order to get the jitter down to that point over there. And as you can easily see, we leave quite a bit of the competition behind us, yeah, in this performance metric. And you see that the big crowd is basically in the 1 to 10 picosecond jitter performance region over here, and not battling for the high grounds there. So in the next few slides, I'm going to explain a little bit how we got our jitter to that point. Well, what my student Thanos Ramkai, what my student did is, here is the publication. I think it's just in the journal published, so you can check it out. So what he did is that, obviously, in order to do 5 gigasample per second, that is above the metastability limit, we need to go into a time interleaved situation. And that means we have an 8-fold time interleaving over here, with a bunch of A to D converters. I'll give you a little bit an idea of how these were built up. Then here gain and offset with digital, and then basically building the output performance. So this is really not, the only novelty over here is what is not there, because very often people have here a buffer in order to drive this stuff. And I think one of the three major contributions my student made was that he showed that you can live without this buffer at the moment you take very, very good care of designing this bit of your circuit. Now, let me now look at how we did the clock tree in order to get the jitter as good as it got. So this over here is the clock tree, yeah, and this clock tree adds 11 femtosecond to the 38 total femtosecond that we got from a keysight generator. And I think at the moment we did the measurements, there were only 2 pieces of equipment available in the world with the right amount of extensions to get it down there. So here is the 5 gigahertz differential input. Obviously, you go first into a common mode amplifier to translate into CMOS over here, and that results in the master clock over there. That master clock is divided by 8, and those 8 clock edges corresponding to the sampling moments in the 8 A to D converters need to be aligned and need to be shifted in order to get skew errors out of that. Now that is then realigned over here. Then there is a last shift being there with a capacitor bank, and then this over here is the sampling cost. This little friend over here took 40 milliwatt, which is 25% of the chip power consumption. Yeah. So we are not talking here about microamps. We are talking here only about milliamps. Yeah. So this is really costed a lot of time to do this correctly. And then, very important, you need a PhD level layout engineer. All my students have to do their own layouts, because I basically think that that is the only way to get optimum performance. If as a designer you do your own layout and make sure you know what the details are. So this clock chain drives 8 of these A to D converters, and I'll give you a very short intro in how this is built up. This is basically what people now call a hybrid A to D converter. It is hybrid in the sense that it is essentially a 3-stage sub-range A to D converter. But the 3 stages themselves, each of them is built up as a successive approximation A to D converter. Yeah? So the main structure is that of a sub-range A to D converter with the residue amplifiers over here, but the sub-ADCs themselves are here locally are successive approximation devices. Well, there's a whole bunch of details in here. For instance, in the first one, we sample on the bottom plate in order to get optimum linearity, while in the second and third one we sample on the top plate in order to get good speed. And so there are many more details. I would point you to the paper. We try to explain there as well as we could what we've been doing, but it would be it would take too long to work with that. I should mention that next to Thanos, there's also, of course, Professor Philippe Tavernier, who I think was an earlier speaker in this seminar series, who is, of course, the main promoter for Thanos. Well, just to show that it is real silicon, here is the layout. You see the 3 stars after each other, and the overall sub-range architecture over there. Here are the 8 SARs, and I hope nobody starts to be very angry, but actually here there is a 9th SAR, because the original plan was to do a error correction based on a redundant SAR, but we couldn't get that to work, and so we had to remove that ADC in the end in this design. You also see that the ADCs over here are the minor part of the design. The calibration and the memories are the bigger part, and this is the real thing with bonded output stages. Well, as an industry guy, I insisted that there would be 5 samples measured. You know, these university papers with the golden sample. That's not my thing. You see here the signal to noise and distortion, and over here the 50 femtosecond line. You see that we run into a little bit more signal loss than based on jitter alone, and that is most likely, as we found out, due to asymmetries that we had in the balloon. Yeah, that's what happens. Well, I'm over half of the talk, but I still want to spend a few slides on quantization and talk a bit about mismatch, and then we'll go into the overview. Obviously, as I mentioned in the first slide, A to D conversion is mapping of an analog signal, a time continuous signal. This is a very poor signal that I've just drawn onto this grid of discrete points, discrete in amplitude and discrete in time. And obviously, if you say you have to choose here the points in such a way that you have the optimum following of this red curve, then you end up with this green line connecting the points. And well, you must be blind if it doesn't occur to you that there are quite a bit of issues and quantization errors are associated with this ideal process. Well, that quantization error stuff has been analyzed a lot. Again, I have to fight a lonely fight over here, because I noticed that nearly everybody calls this quantization noise, and I say, no sir, there is no noise there. It is just distortion products that are folded up and down by the sampling process. So for NS1, it's easy. You have a simple comparator that switches between positive and negative. For NS2 to 6, you get quantization errors, mostly at integer sums of the integer times the sample rate plus or minus integer times of the input frequency, and that means that you basically are looking at a grass field of tones in your spectrum. And then above 6, people model, and again, just as the KTC, model the quantization as a flat frequency spectrum with the quantization error energy in there. And then people talk about the quantization to signal to quantization noise ratio of this very important formula that is of course in every A to D converter's mind. But don't forget that even if you do here an 8-bit ideal quantization, so this is computer stuff, yeah, MATLAB stuff, yeah. Even if you do that with a perfect quantization, then note that the third order distortion component from this harmonic is only 75 dB down from its parent value. And that means that for quite a bit of communication issues, this problem cannot be ignored. And you really run into big trouble by simply saying, oh, look here, this is noise, just a noise floor, no more than that, sir. No, 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 be careful, be careful. It is and remains a distortion problem. Yeah. Well, you can have trouble over there, and that trouble comes from not equidistant quantization, and we saw already trouble from not equidistant sampling moments. So the question is, how far can we push this quantization? How accurate can we stay? How well can we guarantee that these points are nicely equidistant spaced? And then, of course, we run into my little hobby, mismatch. And actually, there are within that field, there are a tremendous amount of effects that play a role. Obviously, everybody knows the so-called PVT, yeah, process, voltage, and temperature. But there are quite a bit of other issues that may play a role that give more or less deterministic errors. Then there are errors that can be seen as random, things like line edge roughness, dopant fluctuations, noise, granularity, interface states, and so on and so on. And then there is stuff that depends a bit on where you live, which company you have, whether you call it deterministic or random. If you have a single LNA and there is an inverter in its vicinity, then the crosstalk from the inverter to the LNA still can be modeled as a deterministic phenomena. But if you have a 6 or 8 receiver chains on your chip, on your SOIC, and you have an ARM9 processor there stampeding around, then basically you have to model it as substrate noise. And that's basically pseudo-random stuff. Well, no problem to talk 2 days on this, and if you really want to hear that, then there is from the MEAD in Switzerland, MEAD.ch, there is a class end of September where you can get a whole day of stuff. I'll just concentrate just for your information on lithography and on dopant fluctuations in this talk. First, of course, lithography. The lithography landscape is to a certain extent simple. If you go into the foundries, you will find massively 193 nanometer light in immersion numerical aperture improvement, and that means that for irregular shapes, your pitch must be more than 100 nanometer. And so all these guys that talk about 45 nanometer processes, now forget about it. It's just commercial humbug, yeah. Because in fact, the lithography is always worse than these type of numbers. So the problem is a little bit that in order to break this barrier, we need something else. Obviously, there is the EUV, and in case you have say 125 million US dollar available, well, if you don't have that available, then this is not an option for most of us, yeah. But basically, going to 30 nanometer means that roughly spoken, your lithography limit goes down to 25 nanometer pitch, yeah. There are other ways to do that, to get a pitch better than that. And the idea is, okay, we have 100 nanometer pitch, but if we print not one layer, but we print the layer in 2 or in 3 steps, we can basically get to a better pitch. So if these 2 green lines over here, if these 2 green lines have a pitch of 100 nanometer, then the fact that I have before that inserted over here a first deposition of the same stuff, say polysilicon lines, then basically I can go down here to 50 nanometer, and if I do it with 3 times printing this material, I can basically go into say the 40 nanometer pitch area. The obvious problem is, of course, the overlay. How accurate is the yellow aligned to the green and to the orange over here? Because that is then the limiting factor. And really, if you go to the manufacturers and you ask them, please, what is your overlay? Then you will get a very nice big smile, but nothing else. Yeah. And there is a third way that is very often used these days, and that is not to trust the ASMLs or the Japanese companies, but to trust nature. And so what you do is you will have here a structure, but this is not the structure that you're interested in. What you're interested in is grown on the sides of this structure. So here you grow spacels, and then you remove the structure, and you basically get this. And it's obvious that over here now you have twice the structure density than what you got there. Then you need to cut it a little bit and pattern it a bit, and you basically have a so-called self-aligned pattern. For every process below 28 nanometer, and sometimes including 28 nanometer, this trick is used. But that trick has a little disadvantage. Because, oh, let me go one back. Because it's obvious that over here you have a left side and you've got the right side. And now the question is the left side equal to the right side? Now, it turns out that that is not so simple. This self-aligned patterning is, of course, massively used for FinFETs. And then you obviously see over here that this fin and this fin differ in dimensions. Here at the bottom, you see 14 nanometer and 15 nanometer. And here in the top, the difference is even a little bit larger, is 1.5 nanometer. Yeah? So the odd-even effects are rather strong, specifically in FinFETs. And that means that in FinFETs, you always have to design taking care of making sure that you have equal number of odds and evens in your sensitive stages. We are at this moment looking at the third generation FinFET. The first generation had this tapered view, but the problem is that the threshold voltage is now depending on this distance over here. And this distance is smaller than that distance. So what you would see is that the current would be flowing at low gate voltages over here and would then start stretching out into this direction, which gives all kinds of weird curves and strange things if you want to use it in the analog domain. So the engineers started to really try to get that tapering away, and this is the latest part. And there's still some difference, but basically this is this is the best that you can get at this moment. Perhaps it takes also a bag full of money because this is of course only available in 2 or 3 companies. In general, FinFET is better, but because the drain-induced barrier lowering in a FinFET is much lower than in the standard MOS. For us, that translates into 4 or 5 times better intrinsic gain. Yeah, so the basic gain of your output impedance on your input transconductance. You have a much better on-off ratio, and that means that you can live with a lower VDD. The odd-even effect creates dimensional errors that you need to worry about. Threshold mismatch is less than planar, but that is traded against connectivity mismatch, and so I'll show you in a minute that it is not really a big advantage. There is quantization of the devices. There's no W over L tuning possible, so it's either one or two devices, and due to the odd even effect, it basically means it's only 2 or 4 devices, and that is sometimes a problem. The metallization patterns are, and the gate resistances are at this moment a bit of a headache, because some people claim that 40 gigahertz is roughly the max that you can do with FinFET. Whether that claim is standing over the years is not yet clear, but that is what is the opinion at this moment. The other issue that we face with accuracy and that I would like to discuss next to lithography is, of course, the fluctuation problem, the charge fluctuation problem. If I want to build in an A to D converter equal elements, equal resistors, equal capacitors, equal currents, then in the end I will end up with something like this as a pattern. This could be a resistors, capacitors, current sources, or whatever more. And the question is, what limits the accuracy of such a structure? So this is intentionally all the same, but it turns out that it is not. Now, the basic reason why we face a problem is that we simply reach the level of discrete numbers. Yeah. So essentially in a 65 nanometer transistor, there is roughly 100 dopant atoms, and the problem is it 103 doping atoms? And what does the neighbor do? Is that only 98 or 95? And so basically the problem is, if we have perfect cubical structures over here, and we fill that with for instance dopant ions, then this number of dopant ions is different from this number of dopant ions, despite the fact that the dimensions here are perfectly equal. That's an effect that we see in many places in a modern design. So modern processes all use metal gate, and the metal gate grains show different work functions depending on how you approach the lattice of this titanium nitride type of structure. And that means that you see over here, this is an Intel photograph. Here there was a coloring method used where you see a high, a medium, and a low work function difference. And that essentially means that you get here all kinds of issues, and that if you do the math for that, then you end up with the same formula that I proposed some 30 years ago in my mismatch paper. And that means that also today we face this ugly dilemma, because what we want in A to Ds is to get this guy down. We want the spread of, for instance, the threshold voltage or other parameters, we want to get that down. But in order to get this down, I need to increase the area. And that means more area means more accuracy means larger area, larger capacitors, and higher power. And so this is the ugly dilemma that until now has not really been broken in design. There are more issues with this same phenomena. This is a little bit curious, but very today's problem, and that is, of course, with the EUV lithography. So here in this photograph, you see an array of contact holes. This is a contact hole over here. But if you print this with an EUV machine, then the EUV light, the EUV photon, has 14 times more energy than the regular EUV, because that simply is seen from the ratio of 193 nanometer wavelength to 13.5 nanometer. That's a factor 14 difference. Now, I need only a few photons. That means I run into the Poisson distribution, and you get exactly the same issues as in threshold voltage mismatch, capacitor mismatch, resistor mismatch. But here it is very nicely illustrated, because you can see that this quantization of photons in this case is very clearly seen. You see here all the potential variations in number of photons that are used to print each of these devices. Yeah? Very nice example of discretization and of getting into the same problem as we saw with this paper some 30 years ago. Well, see here my career. This here is me 40 years ago. Yeah, basically 2 micron processes. Yeah, roughly 40 to 50 nanometer gate oxide thickness, and then roughly spoken, here you see the development of the parameter AVT over those processes, and you see that essentially this parameter goes nicely down, and over here are the FinFET devices. The problem, however, is that this here is basically, AVT is basically the value of a 1 micrometer square transistor, and that is the case for each of these transistors over here. And that means that I fool myself a little bit, because why would I use a 65 nanometer process or a FinFET process when I will stick to the same area as I used 40 years ago? Yeah. So basically, this line, and we will see it a little bit later, is going in a completely different direction if you use the scaling of the process. Is this also favorable over here? Well, here is the FinFET. Here are the FinFET results presented on the transactions of electron devices, and here is the AVT of these devices. Yeah, this is caused by work function fluctuations and oxide charges. Yeah, and if I now add to this graph, I add the line that is valid for an old-fashioned 18 micron CMOS process, then you see that with 18 micrometer CMOS, you're not that bad off. And if you now keep in mind that, roughly spoken, an 18 micron process has a 1.8 volt power supply and accordingly large signal, then obviously even today I advise my customers, if we want to build a high performance analog circuit, I advise them to look into 0.18 micron processes, because you will see that for real analog performance, of course digital is a different story, but for pure analog performance, this is really not a bad idea to work in that. Well, just a little warning that I want to issue here. Why is this mismatch stuff such a bad enemy to fight? The reason is because the mismatch, and I have to step over the math over here, but the mismatch description is mathematically a function that is basically e to the power minus x squared. Now, e to the power minus x is already ugly, but e to the power minus x squared is really, really bad. And that means that if you run into Gauss-type errors like mismatch, then you see very, very sharp decay in yield. As you can see here, for instance, this is the offset of a comparator, for instance, and here you are at an offset of say 0.9 millivolt, and you still have here 95% yield. Here you are at an offset of about 1.2 millivolt, and you've got nothing. Yeah, and the reason is that all these error mechanisms go with this very bad mathematical behavior, causing this tremendously steep yield loss curve. And that means that error correction and all that kind of stuff doesn't help you much in this way. If I summarize a bit the mismatch stuff, then we have for most transistors we have this type of description. I put here a bit of a value and the reference that's given there. It is equally valid for the base of a bipolar transistor. Depends a bit on what type of bipolar you use, a SiGe or say a parasitic transistor. And then it turns out that the CMOS parasitic transistors have a much lower matching than the advanced high-speed transistors. Interesting thing to remember. Resistors differ for diffused resistors of poly resistors. So I still don't understand why anybody still designs stuff with polysilicon resistors, because they are really, really bad guys from matching perspective. And then obviously the capacitors. And the capacitors have by far the best mismatch characteristics. And that means A to D converters, for now and in the future, if you need accuracy, always go for capacitors, because that gives you intrinsically the best values. What to do when you have problems, when you have errors? Well, actually, I think there are only two ways that people figured out, except of course for doing your own layout. Hey? That's of course really number one. Hey? Do your own layout. But getting rid is basically either a form of modulation or a form of calibration. And modulation means that you rotate elements over time, that you move the errors to other frequencies. Calibration means that you measure and correct. Yeah? And examples are dynamic element matching over here, data weighted averaging. Examples over here are auto-zeroing, which you always must avoid. Yeah, digital correction, analog tuning. Well, with each of these there are issues. When you use modulation, then you run into downmixing problems. It's another sampling mechanism. Yeah. While you do calibration, you need correction over there. Sometimes you run into KT over C problems. Yeah. Limited by the accuracy that you can provide, and so on and so on. So basically, this is not a real menu that you can say, okay, I've got this problem, I know what to do. So basically, consider very carefully which technique is applicable if you want to get rid of errors. A good example is the time interleaved design of A to D converters, where I come back to the paper of my Leuven student. In such a time interleaved structure, where you basically got A to Ds, DSPs, and D2As, you've got all kinds of mismatches like the offsets over here, which translate into this nice little pattern at the output. But you got more. You got input bandwidth mismatch. You got gain mismatch. You got layout timing mismatch, you got parasitics, and so on and so on. I can discuss this endlessly, but just let me give you and point you to a paper that I really like. That is a paper by I think it was a Broadcom engineer, Brodorini, some 4 or 5 years ago. And I think he really understood what he was doing. He used, in his front end, he used passive sampling. So no op-amps, just as my student, we avoided here to do any active manipulation on the circuit, but basically differential sampling, optimize there for KTC noise, and make sure that your bandwidth is adapted. Then here, a ping pong structure, which basically is the nickname of a 2 times interleave. Why is this optimum? Now that is optimum because a number of errors appear at the half of the sampling frequency. And very often you're not interested in that because you're only interested in that range. If you would have here 3 of them, you might already have here components that fall into your range. So this is very smart to do this with a ping pong architecture. Then the MDAX structure allows you to reduce the amplitude. And that means that here you can concentrate on a relatively small circuit and optimize the entire accuracy of your system. You should invite Professor Willy Sanson from Leuven. He writes really phenomenally nice with this mechanism. I am only a poor student there. So he crunches the amplitude problems here, and then what is left over he amplifies, and in a very relaxed way he uses the optimum conversion technique for an 8-fold multiplexed successive approximation there. Low power, easy in calibration over here, and you can extend the resolution to your desire. So I think this is a interesting paper, and I always ask my students to review that because I think it is you can learn a lot from that. Well, basically rounding up. Well, I started with a few fundamentals of A to D converter. We looked at Heisenberg here in the upper corner. We looked at thermal noise. We checked jitter, and we see that there's a whole range over here where we will not penetrate with sample data systems soon. Well, we looked at calibration and mismatch stuff. Basically, calibration is very popular amongst students. Everybody needs to calibrate everything else, but I basically advise against too much calibration because you will soon find out that it has in the applications very often a number of big disadvantages. And then finally, where are we? So these red lines are based on the Walden figure of merit, and you can easily see that if I want to build a 10 megahertz 12-bit A to D converter, then Walden tells me that it will take practically it will take a milliwatt to design that. From a thermal noise perspective, I would need only a microwatt. So implementation loss-wise, I am here already a factor 1,000 gone, and so there is still quite a bit of area to win between the practical and the theoretical problems. Obviously, with 12-bit 10 megahertz, I am already rather close to these two more or less fundamental limits, either the mismatch of your components or the jitter mismatch that will limit my real progress only to a factor 2 or so in this design. That means that you can also map your A to D principles on this. Obviously, down here we have the flash A to D converter. Stretching it over here runs into the metastability problems. Here we have a bit higher performance from signal to noise perspective. That is essentially here limited by sampling jitter. But if you go to higher signal to noise ratios, then you either run into passive component accuracy or into the jitter of the D to A converter, because you are then obliged to move into sigma delta over here. Delta sigma seems to be the better word, some people say, but then basically here you are limited by the D to A component in the A to D that keeps you up all night. Sorry. So just overviewing, we looked a bit at jitter. At this moment, 50 femtosecond is best in class. I still believe there's some space to win. Metastability is something that we will run into already today. You see a lot of papers that run into that type of problem. It will become a more and more important limiting factor in a number of designs. Best matching performance is obtained by capacitors. FinFET hold promise for gain-dependent architectures, but I would not I would not expect real improvement from that. And as a whole, technology is not going very fast at this moment. And I think SOI is a candidate specific for analog applications. Well, my dear friends, analog to digital conversion stays a key function in all modern systems. So designing A to D converters is still a very, very profitable business. Fundamental limits are given by time and component accuracy. We looked a little bit into that, saw jitter, saw metastability, saw mismatch, saw lithography. Yeah. Technology impact is dictated by parasitics. That means that a good layout is still very, very valuable. All advanced converters now use multiple A to D conversion systems and are therefore called hybrid. And I still look ahead with a lot of joy because I see still quite a bit of things going on that make me pretty happy. I'll send over the slides after this presentation so you can have a look at a number of the stuff. And obviously, you always can look into one of my books. I would not buy one of these books. Actually, I make nearly no money of that. And moreover, I just signed the contract with Springer. Although I don't make any money, I still have agreed to do a fourth edition that will be on the market next year. Yeah? That's it. Thank you for listening, and I'm open for questions.
Thank you, Professor Marcel. It was really nice presentation, right? Enlightening, and we looked this in the complex block, right? The ADC from a system level perspective. This is really interesting. A very good point. We have a big audience, and still people were really looking with very good comments on your presentation. Right, very nice talk. And I have several questions here, so let's jump directly to that. So the first question is from Rafael Cardoso from Sergipe State, which is at the northeast of Brazil. And the question is, do you have any expectations about the field of analog to information converters?
Analog to information converters. I think that what you mean here is all kinds of converters that more or less try to go directly from the physics to the from the physics domain into the digital domain. So basically avoiding to convert to voltages and currents in between. For instance, time to digital conversion, capacitive to digital conversion. This is not a new theme. Okay, it's talked about a lot recently, but it's really not a new theme. Very, very old professors will recall that one of the most simple ways to transfer, say, sensor data into a system is to modulate an oscillator and then watch the frequency. So that is already an analog to information converter. So I must admit that I do not see a fundamental novelty except for the term. The term is new.
Okay, so the next question is coming from Pedro Toledo, who is at Twente University at this moment. And the question is if you can comment on the KTC noise cancellation.
I don't know.
The possibility of that.
Oh, the possibility of that.
Yeah, maybe the possibility of that, because we were working with noise cancellation on the LNA, for instance, and yeah. I think maybe it's coming from this the question.
Okay. Yeah, I just wanted to say directly that in Twente I worked with Professor Bram Nauta, who worked for me once, and now I work for him. That's how life goes. And he came up with a very nice idea where I can spread a little bit of gossip, because he came up with this idea. The idea is that if you have a MOS transistor, that the noise that you find in this transistor, on one hand, is leaving the transistor on the drain side, but the current that leaves on the drain side is the same current as leaves as comes in on the source side, and so obviously you have the same noise available on source and on drain side. And despite the fact that the noise is completely random, you are able to play a few cancellation tricks there. And I just recently heard Professor Bram Nauta explain that his idea is in half of all the mobile phones in the world. Well, I didn't count them, but actually I only have since a year myself a mobile phone, and I still have to switch it on one day. But that is an option. Yeah. In the larger sense, I do not see much options to go into KTC noise cancellation. So in an LNA, it is a possibility, but there are many papers who try to do some noise cancellation or so on with rerouting capacitors, but all of that fails.
Mm-hmm. Okay, thanks. Next question is coming from Roger Zamparetti, who is at Delft University at this moment, is a Brazilian guy. So which CMOS technology node has been shown to be the sweet spot for the high-speed ADCs? So that's the question.
Good. Roger, I expect you in my class early February, eh? Then I'll answer the question. The answer to the question is, if you want to, I think I answered it a little bit during the talk already. I prefer the 0.18 micron node that allows to have something like 3 times more amplitude than the say 28 or 40 nanometer nodes, and its characteristics are way better. Obviously, you pay that with a very poor digital density.
Okay, so Roger, you have an appointment now, right? Professor Sergio Bumpi is asking about And the current FinFET designs, which are the errors that you classify as Gaussian square distribution errors? Which are the dominant for ADC resolution or speed at the FinFET point?
Two questions.
Yeah.
Well, independent, whether it's FinFET or planar transistors, all the mismatch type of errors that are coming from Gaussian distributions, like the threshold mismatch distribution, the mismatch of capacitors, the mismatch of bipolars. All these mismatches are having this squared e-power distribution. I just was that's nothing peculiar. That's just a standard error function mathematics. Yeah, and all of these have this distribution. So at the moment, you see this Gaussian distribution curve popping up. Directly be alerted that errors that behave with a Gaussian distribution, independent whether it's mismatch or noise or any production failure in designing access or mechanics or whatever more, all of these will show the same problem with the yield. The dominant, which are the dominant parameters, I guess, for ADC resolution or speed?
Yeah.
Now, for speed, the problem is metastability. Yeah. And for resolution, well, the question is, do you want to go into component type ADCs like things like pipeline structures or so, or do you want to go in oversampled structures? Well, if you go into oversampled structures, then the resolution is virtually unlimited. Yeah, I've seen oversampled A to D converters with a bandwidth of say 100 Hertz that is used for 22 bit of effective resolution, which is used for monitoring earthquakes and other geological stuff. So that is basically the resolution is just a matter of getting the bandwidth down and getting the oversample factor up. At the moment, you run into problem. Then basically it is because you have jitter in your feedback path.
Okay. So next question is coming from Professor Gilson Wirt. Starts with a comment. Thanks for the great talk. Did you look at jitter variability among devices? I mean, you report a jitter value. Did it vary from one chip to the other? Did you relate jitter variability to development area?
The device area.
The device area. Yeah.
Thank you very much, everybody, also for the questions. There is a two-sided answer. Did it vary from one chip to the other? That depends on what jitter mechanism is attacking you. If you have a time-varying mechanism, like your jitter is coming from crosstalk of processors or from poorly designed buffers, thermal noise, then basically the instantaneous jitter values will of course differ, but the ensemble values, so the sigma, will not vary from one chip to the other, provided that the noise is the same, the crosstalk is the same, the spurs are the same, and so on and so on. if you look, for instance, more specifically to the example that I gave on time interleaving, then that is very strongly dominated by things like offset. And then you run into basically this AVT divided by the square root of the area problem. And then you indeed can see that with relatively low number of time interleaving, you may hit a good sample and you may hit a bad sample, and essentially, indeed, the device area is a way to attack that problem. Well, please come back to me on email if you need a more specific answer. Yeah.
Oh, thank you. We have still two more questions. Well, we have many more questions, right? But let's stick with these two. From Bruno Canal, who's a student at ADCs here at our university, right? Professor, thanks for the great talk. The question is, could you comment a little bit about the relation of input refer noise of comparator and its limitation on the ADC resolutions?
Well, I'm going much deeper in my class that Roger Samparetto will enjoy in half a year from now. So after that, you can ask him. I see a lot of errors being made in comparator design, which basically boil down to the problem that input noise really is a limitation. Yeah. But I think if you look at it from a more general perspective, let's say all the not sigma delta A to D, so everything except sigma delta is nearly always using a sampling mechanism, and therefore a capacitor, and therefore KTC noise. I think at the moment you run into the problem that your input referred noise of your comparator starts to match the KTC noise, then you really should scratch your head and think on what went wrong, because that should not really happen. So my statement here is only in extreme situations your input referred noise of your comparator is a limitation for the ADC. In many more other cases, a well-designed A to D converter should basically be limited by the KTC noise of your sampling mechanism, and no more.
Okay, so well, now we have the last question that's coming from Marcelo Dal Alba. Inspiring presentation regarding FinFET mismatch characteristics. Could you point classic examples where, first, connectivity mismatch degrades and voltage threshold matching improves in analog performance?
Is this a question about papers?
Yeah, well, I think good references on that. Yeah.
Let me address the last one, because the mismatch degradation by connectivity is something that we all know is a real issue, but where you very little reference you made in papers. The VT matching is another issue. And I would say that at some point in planar CMOS, we were stuck with, for instance, scaling SRAM design. Basically, SRAM design could not be further scaled because the errors that you got from the threshold mismatch were so big that an array of millions of SRAM cells would contain too many too many errors, and then I return to my yield plot there, where I think Professor Bumpy commented on. That was basically a killer. And if you now look, you see that SRAM design is now progressing further, yeah, but by the use of FinFET design. But apparently connectivity mismatch is not really an issue in an SRAM design, because the speed over there is generally spoken not really an issue.
Would you like to take another one or two questions?
Yeah, but before we do that, because I forget to ask that, shall I send the PDF to you, Professor Ferreira?
Yes, yes, that will be fine.
Yeah, but
then you can distribute. Yeah.
You can distribute it to the people who watch this this class. But may I ask to everybody that receives one not to put it on internet?
Yeah.
I want to educate more people.
Yeah. Okay,
And
okay.
so please do not put it on public internet if possible. Eh?
Okay. Okay. So
okay, a few more questions.
A few more questions. Yeah. So this from Paulo César Comaceto Aguirre. Great talk. Considering a 180 nanometer process, which ADC topologies can be explored for research purpose? Can you comment on that? Like
on the speed and resolution.
Yeah, speed and resolution. Yeah.
Well, I think that in the presentation, like this one, like this plot and this plot, you can find already a bit of an answer to the speed and resolution, and you can also see why there is a problem. Yeah, let me briefly address the speed problem, the speed and the sampling jitter. You know, when I was at Stanford, I had the joy that every now and then guys like Tom Lee would take me out for a good dinner, and during one of these dinners we discussed jitter, and Tom Lee came up with a very interesting argument, and he said, we are talking about 100 femtosecond jitter, but the guys from Professor Miller, the optical professor there at the time, they start laughing at me when I say 100 femtosecond jitter, because they talk about 1 femtosecond jitter. And so we came up with comparison between optical and with electrical. And if I would be a young PhD, I would see there a huge opportunity. How can I translate the 1 femtosecond jitter that you can achieve in the optical domain into a sampling mechanism in the electrical domain? Yeah, there is I think a very nice idea for, I think that will be valuable research. The question, ADCs topologies that can be explored for research purposes. I would say stop that. Don't try to be smart in an ADC topology anymore. There is so much effort being spent already on pipelines, on SAR, on flash. The only way forward here, the only thing as a useful research project is to really step aside. Yeah. So one of the projects that I did with the University of Cork was that I think most of you know what a pipeline A to D converter is. Basically, a pipeline uses an input stage, subtracts a reconstructed signal from the input signal, and then amplifies it and moves it forward. The problem with that input stage is that you take a sample. Because at the moment you take a sample, you basically introduce KTC noise. And so with that University of Limerick, we worked for 3 years on a to D converter that had a analog way to implement the first stage of a pipeline. So no clocks in the first stage. An analog variant of the first stage of the pipeline, fully analog. And well, we managed to get that and get some real interesting performance. But then you directly see the problem with A to D research. We were sponsored by a local A to D company, which has more places all over the world. And actually, if you say AD, then you have already the first 2 letters of its initials. And they looked over our shoulders. And if you go to the ISSCC of 2017, the second presentation, Shibata, you will find that idea. And unfortunately, the authors of that paper completely forgot about us. But okay, that's part of life. But if you look at the Shibata paper, I really think, and I really mean that, I really think these people missed a huge opportunity to make some progress there. So that could be an idea to work on that.
Thank you. Very, very nice. Very nice. Well, so the last question here is, sorry, this is my limited compared to noise. Yeah, so I think it's, we have already commented on that, right?
Yeah.
So, well, thank you very much. It was really a nice pleasure to have you here. We still full audience here, right?
How many people do we have?
At this moment, we have 61 people attending. We got to much bigger peak at some moments, right? And it was really nice. So thank you very much for this nice talk. So to the people that are still there, just would like to invite you for the next presentation that will be on the 3rd of September with Professor Paolo Grovetti from Torino University, Polytechnic University of Torino, that will talk about analog processing by digital circuits, fully synthesizable ICs for IoT interface. So we're also, again, at a system level point of view, right, but with a very different perspective. Professor Marcel, thank you very much for coming and joining us. It was really nice to have you here.
Okay, thank you very much, and perhaps till another time.